So in the second section, we're going to go through the basic reduction part of the pipeline tutorial. So this is the second section here, and so this will be doing BVGRI reduction without subtraction. We'll do that in the later part. This is the most basic version of the reduction you can do, and so there are these there are these four main parts that are the main steps you have to do. You have to generate PSFs for the images, you have to measure their instrumental magnitudes, calibrate the 0 points, and then calculate the magnitudes. So those are the four primary steps to do, and then there are also supplemental steps to check the quality of each of these four steps. And I want to say before I start that if you go to the GitHub and then you go to this documentation section, there's a manual. This was mostly written by Azalee. I'm going to do pretty basic steps. I'm not going to talk too much about extra arguments and stuff you can add on. But this manual section for each stage, this lists how to fix things if the step failed, arguments to check out. So this document has a lot of knowledge in it, so I would refer to this if you have questions, or you can also always ask the pipeline channel in the GSP Slack if things aren't working and you want to troubleshoot. But okay, so we'll go through this section. Okay, so again, I'm going to start up the pipeline, or start up the Docker container. So the database is started. Now I'm in my Docker container. And so, like I say in the tutorial, I strongly recommend having separate directories for each object that you reduce. So I have this data reduction directory, and then inside this directory, I have separate directories for each object that you reduce. So this is because the pipeline generates a lot of auxiliary files when it runs, and so if you're running multiple reductions in the same directory, you can end up using files intended for one object accidentally on another object, and then things get all messed up. So I'm going to go into my 2017 CBV directory because this is the first object we're going to reduce. So in the pipeline, for historical reasons, the main script that you call is lsc loop. So all of the commands that we run are going to be lsc loop commands. And the general syntax I use is lsc loop -n for the name of the object. So this first object is 17 CBV, and then -e for the epoch. So this is the first epoch, 2017, 0517, year, month, day. And you can see there are 12 images for that epoch. So our typical UBV GRI sequence with 2 images per filter. This epoch argument, you can use one epoch, or you can put in a range of epochs like that. So these are the 2 epochs that we'll reduce in this tutorial, although in this first basic reduction step, we're just gonna do this first epoch. Okay, so the first thing we have to do before we start going through the reduction is we're gonna open up a window of DS9, so DS9 space ampersand, so it will run in the background. Okay, and then we're going to, just to show you what this stage looks like, we're gonna just select the U-band data, so you can use -F to specify a single band, or you can do -F landalt to get UBV, or -F Sloan to get GRI. So we're going to get the U-band data, we're going to run Psf Stage, Each different stage that you run is specified with -s. And we're also going to run this with the show command just to show you what the output looks like. Okay, so this is what the output of the Psf stage looks like if you run it with the show command. So in the DS9 window over here, this is the image, and then all of the stars that it knows and that it reads in from the catalog are circled in gray here. So you can see there are a lot of stars in this field. The stars that are circled in blue are the stars that it has picked to average together to make the PSF. And you can see what the PSF looks like in this IRAF window here. So by default, it uses the Gaia catalog to select stars and select PSF stars. We changed this. We made that the default pretty recently because it mostly does a pretty good job of excluding H2 regions and galactic cores and stuff. In this case, there are 2,086 stars in the Gaia catalog for this field, and you can see by default it has picked 6 of those to average together into the PSF. So you can either press enter to say it's a good PSF or press N to say it's a bad one. So in this case, I'm going to just kill stuff with Control C, and then I'm going to generate PSFs for all of these images. Specify the name and the epoch, and then just to keep things consistent, I usually specify the images in the first part of the command, and then the stage, which in this case is the PSF stage, and then any additional arguments specific to that stage after in the second half of the command. So some arguments that I'm going to use in this case are this field option. So the Gaia catalog for this field is quite crowded. It has 2,000 stars. It took like 45 seconds to make that PSF, which is a little slow. I'm going to switch to the APAS catalog because that has fewer objects, so it'll run quicker. You can also specify the number of stars you want to average together into the PSF with n stars. So I'm going to up that to 12. And then when it picks the stars, it can exclude things based on their maximum counts or their minimum counts in the stars profile. So I'm also going to specify data max 75,000 to exclude bright stars. And then this dash capital F argument is the force argument. And so this will rerun the command even on stars that have successful PSFs, just to make sure that everything is generated consistently. So I'm going to run that and let that go. Okay, so that command is finished running. Just an example of what it looks like for the successful output. So it is using the catalog, picking some stars, tells you how long it takes, updating the database with the PSF name, although none of these other stages have been done yet. So just to look at that, we can just pull up the data again, and then you can see this column that specifies the PSF now has those PSF file names in there instead of just X. So that means that it was successful. If we want to look at the PSFs, we could have run that stage with -- show, or you can just run it in batch and then run this check PSF stage. And we're also going to use this no IRAF flag so that everything's in Python. And so this generates similar plots to the show option in the PSF stage, except now these are matplotlib plots. So again, catalog stars are in red, and stars that have been selected for the PSF are in blue. So you can zoom in, look at individual ones if you want to. this is what the PSF looks like, and this is also manipulatable, so you can like spin it around to look to see if anything looks weird. In this case, things look pretty typical. You know, it's like nice and symmetric, looks pretty Gaussian, no like weird bumps or anything. Just to explain these options here, if you just press enter, it'll say, okay, that's fine. If you press N, then it'll delete the PSF, so you can redo that stage, generate a new PSF. If you press B, that's for if the whole image is bad, like something disastrous has happened, the shutter got closed or something. If the whole image is unrecoverable and you should just exclude the entire image from reduction, then you can press B. In this case, the PSF looks good, so I'll just press enter. And then we can look through these. It also lets you check out the images, see if anything's weird in the images. So a lot of time spent during reduction is spent in this stage looking over the PSFs and making sure that everything is looking normal. So these last PSFs are looking a little lumpy, but we'll keep going through with it. Okay, so all our images have PSFs now, so the next stage is to measure their instrumental magnitudes. So that stage is just called PSF mag. Okay, so that's all done. I usually don't look at the output too carefully, but just to go through what it looks like. So it goes through, it iterates to center the PSF on the supernova, and then it updates the database with the PSF mags and the aperture mags. And so if something has gone wrong, usually one of these rows doesn't get updated correctly. It'll say update FOTLCS at PSF mag to 9999, and that means that something failed. But if we look at our images again, if we just pull up the list, then these two columns over here, these are the PSF magnitudes and the aperture magnitudes for our images. And so these are all filled in, so it looks like everything went okay. And then there's another stage, check mag, that lets you look at what that PSF, how the PSF extraction looked. And so this image is now centered on the supernova. The left is the image, and the right are the residuals after subtracting off the PSF. So in the ideal case, this right image should just look like flat noise. In this case, it looked like the PSF got extracted quite successfully. So again, a lot of time spent reductions is spent in this stage checking how the PSF extractions went. And then you can do the same thing again. You can mark bad extractions with N if you want to redo them. And so I'll just look through all these. This is clearly not ideal. The PSF has some flux left over that it didn't subtract out. So I would probably mark these as bad and redo them if this were a real reduction, but we'll just go through. These don't look terrible. Okay. Great. So we have done the first two things. We've generated PSFs and PSF and instrumental magnitudes. So the next thing we have to do is 0-point calibration. So you have to do this twice. You have to do it once for the Landolt filters, and you should do it with many different filters together in order to get color terms correctly. So we're going to pick the Landolt fields, the Landolt filters, excuse me, run this 0-point calibration stage, this zcat stage. Then you can specify which field, which catalog you want to calibrate the stars to. So APAS has land-alt magnitudes, so I'm going to calibrate the land-alt images to the APAS catalog. It says it can't find a catalog for U-band. That's why you have to do U-band separately, because APAS doesn't have U-band in it, and there's no all-sky U-band catalog, which is a real bummer. But so that stage ran pretty quickly. Everything looked normal. It's updated. It's calculated 0 points for and color terms for each of the images. So we'll just do that again with the Sloan filters. If the object is in Sloan, you can specify -- field Sloan. But in this case, 17 CVE isn't in Sloan, so we'll just do that with APAS again. So the stage runs pretty quickly, cool. So now if you just pull up the images, then this column, it's a little hard to see because it's getting split, but this tells you what catalog you've calibrated stuff to. So I've calibrated all these images to the APAS catalog. These first two, there's still an X in this column. That's because those are the two U-band images. But it looks like these all got successfully input into the database. And so the last step is to run the mag stage, and that calculates the actual magnitudes. Okay, cool. So these are the magnitudes and the errors for each of these images. They all got successful magnitudes except for these first two U-band images. And so the last thing I want to say is, if you want to look at your light curve, you can run the get mag stage. You can specify what type of magnitude you want to do. So if you do type mag, that'll do like actual apparent magnitudes. You can also specify type fit or type pH if you want to look in magnitude or aperture magnitude space. But we'll just look in apparent magnitude space. And then I'll run it with the show command so we can look at that. So here's my light curve for this one epoch, BVGRI. This is an interactive plot, so if you click on any of these things, it brings up that check mag stage, and now you can see the magnitude is filled in here as well. So during reductions, you also spend a lot of time looking through this stage, looking to see if intra-night points within a single filter are discrepant from each other. That means that one of them is probably wrong, and you should check those out and redo them. Also, if single nights are outliers, it's pretty easy to select these, and then you can, for instance, if you select a point, you can press D, and then that'll delete that point and let you redo some of the reductions. Then press enter to exit. I should specify, so I just marked one of the images as bad. So you can specify, or you can pick out images that have bad magnitudes with this -b argument, so -b mag, to pick out like this image that's the one that I just deleted that I want to redo, and it also picks the two U-band images because those also haven't been calibrated yet. So this is a way to go through and redo points that you mark as bad. You can just pick them out with this command and then rerun whatever steps you want. The last thing to say is that this get mag stage is also how you output files. So it's how you output light curve files. So you do the -O for output. So -O and then whatever you want the file name to be. So 17 CPU tutorial. And then if I open that up, that is what I send off to collaborators when they ask me for data. Okay, so that's going through the basic reduction. So again, the main steps there are the Psf stage, the Psf mag stage for measuring instrumental magnitudes. And for both of those, you can check on how things are going with check PSF and check mag, and then the 0-point calibration stage, the secant thing, and then also the magnitude stage for final magnitude measurements. So those are the four main steps with checks for basic reductions.